Good afternoon. Now that we've heard in the morning a lot about all the good things we can do with richer sets of data from our sensors and how we can apply AI to actually make sense of it, I'd like to focus in this talk at the sensor level. So how do we make sure that sensors see further, detect smaller objects and separate smaller objects from larger ones more reliably? And I'll talk about some of the key innovations that are underlying. So starting off with a quick market outlook, we'll then move to the advanced use case drivers, and then we'll see the key enabling technologies, which in particular involve 28 nanometer RFCMOS single chip integration for radar and high resolution 4D imaging radar. Starting off, the ADAS market outlook. So what are we looking at? So basically, this is a view of how we expect the market to evolve by 2030. And we have basically segmented this into the different levels of autonomy. And by 2030, we do see some growth in highly autonomous vehicles, level 3, level 4, starting from a small base. So expect 2030, this is going to be still a relatively small share of the market. At the same time, large growth is expected in the level 2 plus segments, driven by, on the one hand, new safety regulations, on the other hand, by new comfort features. And you may have heard most recently BMW announcing their capability to provide hands-off driving up to 130 kilometers starting November. So this is the category that we are talking about, which by 2030 we expect will assume around 50% of the overall vehicle production worldwide, and which will require a lot more advanced sensors to enable that. And that actually will translate into significant growth in radar sensor adoption. On the one hand, safety mandates will drive fit rate, will drive adoption rate, more cars equipped. Secondly, 360-degree surround radar sensing for enabling new comfort functions will result in more sensors enabled per car. And eventually, the desire to have a richer set of data based on radar sensors will result in introduction of higher resolution sensors for the imaging radar sensors, which is accelerating starting 24 and 2025 onwards. That translates into this S-shaped growth curve we see on the right-hand side, where by 2024 we will see about 2 radars on average equipped per vehicle, relative to the overall vehicle production, moving towards 5 radar sensors average in the long run. So that is the trajectory that we are foreseeing. Now, what do OEMs actually want when it comes to their sensor suite, their radar sensor suite? So this is the picture of what your radar sensor suite might look like for a premium vehicle come 2025, come 2026, with more than 10 sensors equipped, more than 10 radar sensors equipped at the maximum. But the reality is that across different OEMs, and even within some of the OEMs that have a broad lineup of brands and car models, they do not have a one-size-fits-all. They expect scalability, and they do not expect island solution for an individual use case. So where are we coming from? So this is where we are today. So today in 2023, radar sensor configurations mainly driven by safety regulations. So we have typically the front sensor for automated emergency braking and the rear corner sensors for blind spot detection. Now let's look at 2025. In 2025, your average mid-range vehicle will be equipped with as many as 5 sensors, 4 corners and 1 front, to enable those new comfort functions we talked about. And in addition, we see the demand for extended detection ranges, 300 meters and more for the front radar sensor, up to 200 meters for the corner radar sensor to detect objects further out in the distance. In 2025, your premium vehicle, as we said before, will be equipped with additional radar sensors, side-facing, rear-facing radar sensors, will use multi-mode operation, where one sensor has different modes of operation, performs different functions. And then we are adding as well high-resolution sensing, 4D imaging radar, that allows us to detect smaller objects, separate smaller objects reliably from larger ones, see the pedestrian next to the vehicle, see the bicycle rider that is next to a large truck. And these configurations are calling for a scalable platform that allows to really build one on top of the other. And that is actually what we are suggesting. That is how we are suggesting to address that need for scalability. That is with a scalable radar chipset architecture that allows us to cover the use cases from the corner radar through the long-range front radar towards high-resolution 4D imaging radar based on a common architecture with common processing subsystems across and with common millimeter wave IPs across the different use cases for optimum reuse and faster time to market. At the same time, that common platform is using advanced process nodes, 16 nanometer FinFET for the processors and 28 nanometer RFCMOS for radar single chip, and is built on our common NDA of automotive grade security and safety that customers trust. Now, putting this into numbers, that is what the market growth will look like. So in 2020, we had exceeded 120 million radar sensors shipped annually. Come 2025, that growth in 360-degree surround sensing use cases and high-resolution imaging radar will result in more than 200 million sensors shipped. And as I said, in the long run, we expect 400 to 500 million radar sensors will be shipped per year, where in 2022, we contributed close to 50% to the actual shipments of radar sensor chipsets. Now, let's look at the advanced use cases which are driving requirements for radar sensors going forward. And I'd just like to highlight a few key ones that are revolving around vulnerable road user detection, for advanced safety features, NCAP 2025, NCAP 2030 roadmap, revolve around comfort features like the highway pilot, the urban pilot, and traffic jam assist. So what is common to these use cases? So on the one hand, there's the request for longer detection range. As I said before, front radar sensors, we commonly now see requirements to detect objects 300 meters and beyond. What is common? That is the necessity to be able to detect more reliably smaller objects, power two-wheelers, pedestrian, and the ability to more accurately separate small objects next to larger ones, like in crowded urban areas. So these are the underlying use cases that are driving requirements for future radar sensors. And for us, the key enabling technologies that we are pursuing, that we are investing into to enable those use cases are primarily revolving around single chip radar integration, where we have just taken our third generation RFCMOS radar to the market, the industry's first 28 nanometer RFCMOS single chip on the one hand. On the other hand, it's revolving around high-resolution 4D imaging radar that provides image-like sensing capability that is getting close to what a LiDAR sensor can provide at a fraction of the cost. First of all, closer look at single-chip radar integration and the 28 nanometer RFCMOS radar single chip that I mentioned. So what does it do for us, that 28 nanometer single chip, which, sorry, that was too fast, which integrates on the one hand the millimeter wave front end with 4 transmit, 4 receive antennas, integrates on the other hand a multi-core processor subsystem into a chip that fits onto a fingertip. So what does it do for us? Two main things. On the one hand, we see a significantly more compact sensor. So now a radar sensor really fits into a 5 by 5 centimeter form factor, easy to integrate with a vehicle. On the other hand, we have longer detection ranges, allow us to see smaller objects 200 meters in the distance, larger objects more than 300 meters into the distance, allows us to better separate objects, to more reliably classify those objects based on radar data. And RFCMOS and our third generation 28 RFCMOS, 28 nanometer RFCMOS is a key enabler for that. And we've done the comparison between the new generation, our third generation in 28 nanometer, in comparison with our first and second generation that were both done in 40 nanometers. And we see that the 28 nanometer compared to the 40 nanometer or other suppliers' 45 nanometer technologies brings about important improvements in RF link budget, output power, noise figure, interface noise, that results in longer detection range, better separation between the objects, more reliable detection of small objects next to larger ones. But now that 28 nanometer RFCMOS really means a step forward, brings capabilities we haven't seen before. Today, I'd as well like to introduce and add on to that takes us to yet another level of capability for radar sensors, and that is the usage of 3D waveguide antennas combined with direct launch from the chip, which allows us to directly radiate the millimeter wave through the bottom of the chip by means of integrated launchers inside the package to the waveguide antenna that is mounted on the back of the antenna, thereby removing high-speed PCB materials from the sensor and significantly reducing losses that are inherent to classical PCB antennas. And what that does for us, our team has actually benchmarked by implementing 2 different types of radar sensors that are both of them using that same chip, that SAF 8500 28 nanometer RFCMOS single chip. On the one hand, with a classical PCB antenna on the left-hand side, and on the other hand, with a 3D waveguide antenna provided by our antenna partner Huber and Suner on the right-hand side. And as we compare the 2 sensors with each other, again using the same chip in the sensor and using the same type of target, so it's a motorcycle type target with a radar cross-section of 5 dB SM, what we can see is that direct launch into the waveguide antenna, here on the right-hand side, provides a 12 dB improvement on signal to noise versus the classical PCB antenna. Now, first of all, we want to make sure we are comparing apples to apples because the antenna properties are slightly different. Consequently, we have determined that the waveguide antenna on the right-hand side is slightly more directive, so we need to subtract 3 dB, which still leaves us with 8 to 9 dB improvement through routing and coupling losses improvement for the direct launch into the 3D waveguide antenna. But what's the essence? So first of all, we look at the classical PCB antenna and we see that the 28 nanometer RFCMOS single chip actually gives excellent performance, and now we can detect a motorcycle target at 200 meters distance, which is very much improved from previous 40, 45 nanometer generations. And I remark that the yellow color means 100% detection probability. So this is what's shown here. So while we get a very good sensor with PCB antenna, we get an excellent sensor with the direct launcher and the waveguide antenna. And the outer ring here is 270 meters. So you see our detection range extends well beyond that. And while the team is redoing the measurements, we think that 400 meters detection range for a motorcycle target is actually realistic. So this is the benefit we are getting from 3D waveguide antenna with direct launch. And basically, this is what the single chip enables in real-life applications. 360-degree sensing. We get distance, relative speed, we get angle, we get elevation. We have enhanced object detection and classification. We get very good elevation, 360 degrees around the vehicle. So basically a new dimension of capabilities for sensors all around the vehicle. Now, as we take those improvements and we apply them to 4D imaging radar, basically that is enabling sub-degree sensor resolution, that is enabling high-density point cloud generation, very similar to what LiDAR can do at a fraction of the cost. And that enables 3-in-1 sensing, where the sensor is able to see across different sensing ranges, near, medium, and long-range detection at the same time simultaneously. In order to do that, it takes actually many ingredients that we all need to master. And certainly the third generation RFCMOS I just talked about is one element, but we need to combine that in order to get a good system level performance with tailor-made radar acceleration. We need to combine that with algorithms, advanced radar algorithms that we are adding to the sensor. And we need to combine that with advanced MIMO waveforms that allow us to operate all our antennas simultaneously for generating higher number of virtual channels, achieving higher resolution from the sensor. As we do that, we do enable, on the one hand, high-density point cloud generation, as is illustrated here in a dense urban environment. And some of you remember pictures we'd seen in the morning that looked quite similar, where now we get a lot of detail from a radar sensor, very different from previous generations of sensors, that allow us to separate and classify those objects based on radar sensor data. But it's not just the near-range point cloud generation. The sensor, as I said, can operate in a 3x1 sensing mode across a wide range of scenarios. Yes, there is the high-density point cloud generation in the near range, but we as well get very good properties for medium to long range sensing, highway scenarios, as we'd seen before. And eventually, we are as well getting advanced elevation sensing capability to determine the pass-through clearance under a bridge for automated parking applications. And we even detect the moving object, that monorail here up on the elevated structure. With that, that takes me to the end of the talk. There are a couple of things I'd like you to remember. Automotive radar growth continues strong, the triple acceleration that I talked about. Safety and comfort functions are the underlying key drivers that are fueling that growth. The 28-nanometer RFCMOS single chip integration boosts integration level, detection range, improved separation. High-resolution 4D imaging radar provides us with LiDAR-like imaging. And eventually, as I'd shown before, on top of the 28-nanometer CMOS, the introduction of integrated waveguide launchers together with 3D waveguide antennas can take us to yet another level of performance. With that, I would stop here and open it up for questions.